So welcome class, welcome to lesson 2 on acids and bases. In the last lesson we talked about the difference in properties between acids and bases. We also talked about how acids and bases form. We talked about how you would differentiate between a strong acid and a weak acid in terms of how they break up into ions and dissociate. And in this lesson we're going to talk about specifically about pH and neutralization. So the first question is, how do we know if a substance is an acid or a base? Well, we can follow these general rules. So we use what's called an indicator. Now, we talked about what an indicator was in class today, and it's used to distinguish acid and base solutions. An indicator will change color in response to changes in either the acid or base concentration, and it will also, by reading a chart, you will know whether it is an acid or a base. So what type of indicators are we referring to? Well, the indicators are all listed. Some common indicators are listed on the left-hand side. So when we talk about indicators, we talk about stuff like bromothymol blue. Phenolphthalein is a very common used indicator. With phenolphthalein, in acid, the solution is colorless. It looks like water. When a base is added to that solution, or if there's a base in that solution, and you add phenolphthalein to it, it turns pink. It's a very common indicator that's used. Also, another one that's used in labs is universal indicator. Universal indicator is a mixture of different indicators. The fantastic thing about universal indicator is it gives the full range of the rainbow to show different pHs. It's much more specific. There is also natural indicators, blueberry juice. We also have things like red cabbage, lemon. Lemon juice would be another example. And so there's different indicators which are natural indicators. Litmus would be another example. Okay, so that's how we know we can test whether something is an acid or a base. So how do we compare acid and base strengths? We use what's called a pH scale. It's a scale running from 0 to 14. 7 right in the middle is what's called neutral, so it's pH neutral. And from 0 to 7 we refer to, on the pH scale, 0 to 7 refers to acids, and if we have from 7 to 14 a pH of between 7 and 14, that generally refers to bases. How would you know what the pH value is? You would have to look at a pH chart for your particular indicator, and that would tell you, depending, you would reference the chart and you would look at what the color is, and that will tell you what pH range it is. Okay, pH scale is a logarithmic scale. Log scales are used where the differences, the full spectrum and the differences between values is enormous. So instead of talking about it in its real numbers, which are in multiples of 10, a log scale is used. And it keeps the scale very, very small, even though the differences between each one of these pH jumps is very large. Each number is 10 times the previous. So for example, the pH, a pH of 8, we're talking about a very weak base, so Hansel. Now, if, for example, you look at a pH of 9, when we go from 8 to 9, 9 is actually 10 times stronger than a pH of 8. Okay, so as you move away from the center of a pH table, the bases or acids become stronger. Okay, so as we move away from the pH to the right, the bases become stronger, and as you move from neutral pH of 7 to the left, we're moving away from neutral to the left, the acids become stronger. Okay, so that's how you know the relative strengths. pH of 7 being close to neutral, just like water has a pH of 7. And the difference between the pH values is in multiples of 10. We will do an extra lesson on logarithmic scales, but look upon the log of something as the opposite of exponent with a base 10. So 10 to the 1, 10 to the 2, 10 to the 3. And if another lesson is required on log, you will also do it in mathematics. But know that between 8 and 9 will be 10 times stronger. And the question for you to think about is, well, what would the difference be if you moved from 8 to 10? So how much stronger is a pH of 10 than a pH of 8 if we're using the same logic? Okay, so the pH scale is used to measure relative strengths of acidity. Just some common items on the pH scale. If we go back, battery acid is very, very strong acid. Acid rain normally is in the range of about 5, 6 on the pH scale. Common items like lemons, a lot of sour food items are acidic, and they would have, in the range of 3, 4, 5. A lot of cleaning agents, soaps, bleaches, cleaners are basic, and they would have a pH between 7 and 14, right up to something like ammonium hydroxide or bleach, which would be a very strong base, and it would have a pH of 13, 14. Sodium hydroxide you saw from the Coke video today, that would have a very strong pH level of 13, 14, whereas something like sodium bicarbonate would have a pH of 8 or 9, so much, much weaker base. When we talk about pHs, we also have to talk about neutralization reactions, and that is the reaction of a base and an acid. As an acid and a base react, what happens is those relative strengths of each of them. So if you have an acid with a pH of 3 combined with a base with a pH of 12, as you mix those together, it moves towards the center. It moves towards this neutral pH value. Okay, so this number 7 is referred to as a neutral pH. So when an acid is added to a base, we move towards the neutral area. And that reaction is known as a neutralization reaction. And it is just another double displacement reaction. And for all neutralization reactions, it's important to note that when acids and bases react together, what are the products of a neutralization reaction are water and salt. So always water and salt. It is a type of double displacement reaction, so we've talked about different types of reactions. And if it also contains bicarbonate, so it doesn't contain hydroxide but bicarbonate, carbon dioxide gas is also produced. So if we look at an example of one, hydrochloric acid and magnesium hydroxide, we did in class today. Remember, hydrochloric acid will always be an aqueous solution. Magnesium hydroxide, we will have to have 2 hydroxides to account for the fact that it has a -1 where magnesium is +2. When we add those together, we're going to get a salt and water. So we know one of them is going to be water, and so we can account for the fact that we've got a H and the OH here, and what's left is going to be the metal and the halogen. Okay, so the salt in that instance is going to be MgCl2. MgCl2, you should know how to get the ratios. Chlorine is -1, Mg is +2. And so what we would produce here is a salt and water. And then, of course, we've got to make sure that we balance this up. So we can have a look at the magnesiums. Are they balanced? 1, 1. Yes, they are. Are the chlorines balanced? Well, we're going to need to put 2 chlorines to balance up the chlorines. And now what we've got is we've got 2 hydrogens here, and we've got 2 hydrogens on the magnesium hydroxide, so that's 4. So we need to balance up here. We've now got 2 oxygens also, so that's balanced. Okay, so that's a classic neutralization reaction, and you should be able to, as part of this course, move from a word equation to a balanced written equation using formulas. So neutralization is just a specific type of double displacement reaction. So here's some examples you might want to work at. work on. The first one is hydrochloric acid and sodium hydroxide. You can see that a salt and water are produced. And water is just shown differently here. The reason why I've shown water as HOH is so that you can see how the double displacement happens. So this is the HOH, and the H has just jumped across and bonded to the OH, and the sodium has come across to the other side. So it's a double displacement reaction. That is a general statement at the top. Acid and base gives you salt and water, and it's a general reaction for a neutralization reaction. So the neutralization model, just looking at it visually, you can see that the ions from the acid on the top and the ions from the base on the bottom will mix together, and what you get is you get your water. So the water will form, and you also get your salt. Okay, so that's a visual look on neutralization reaction, and it's a model to help us understand and try to think of how that happens. Finally, is there any applications to that? Yes, there is. In terms of chemical spills, when there's a big acid spill, you may need to use sulfuric acid or sodium hydroxide to neutralize that reaction. It's a way to make a dangerous spill less dangerous, is to neutralize it, knowing that you'll only produce a salt and water, much, much less dangerous than an acid or a base. We will talk tomorrow in class about how to do this. An oil spill cleanup, the one that you've just seen, an example would be calcium oxide reacts in water to form calcium hydroxide, and that calcium hydroxide can then be used to neutralize sulfuric acid. So remembering that to get the calcium hydroxide, the base, what did we react together? The water and a metal oxide. So just going back to how we produce a base, we have a metal oxide plus water. That gave us the base, and we can use that to neutralize the acid. Okay, more applications. The wonderful world of perms. Yes, they're used in perming, and the hairdresser applies a base to break links between the hair molecules. So you see this I think that's Phil Spector on the right there with a monstrous demonstration of a perm. And at the bottom, another example will be fire extinguishers used to generate carbon dioxide, which can smother flames. So there's many different applications to neutralization reactions, and we'll talk a little bit more about it in class tomorrow.